Have you ever stopped to wonder how it's even possible to see right through your own skin to the bones inside? It's pretty amazing, right? Well, today, we're going to pull back the curtain on the incredible physics of X-rays. We'll start with how we create this invisible light from scratch, and then see how we use it to build these stunningly detailed 3D models of the human body. So here's our game plan. First, we'll get into the nitty-gritty of making X-rays. Then, we'll see how those rays create a simple 2D image. After that, we'll take the giant leap into 3D with CT scanning, get our hands dirty with the actual physics that makes it all tick, and finally, we'll tackle some of those big questions about safety and how this tech is used every day.
So yeah, how do you take a photograph using a type of light that your eyes can't even see? It's this fascinating process that lets us peek into the hidden structures of our world. And believe it or not, it all starts with a single, super fast electron on a collision course.
Okay, first things first, where do these X-rays even come from? Now, unlike something like gamma rays, which can pop out of radioactive decay, X-rays are totally man-made. We have to produce them, and we do it by taking fast-moving electrons and just slamming on the brakes really, really hard. And this right here is the workhorse that does it all, the X-ray tube. Inside this vacuum-sealed tube, you've got three really important parts. There's a heated filament, called a cathode. That's our electron factory. Then you've got a super high voltage supply to create a powerful electric field. And finally, a heavy metal target, the anode, which is basically a high-tech backstop.
So here's how it all goes down in 3 simple steps. First, we heat up that filament until electrons literally boil off its surface. That's called thermionic emission. Second, a massive voltage, we're talking tens of thousands of volts, launches these electrons across the vacuum. And third, they smash into that metal target and stop almost instantly. It's that sudden, violent deceleration that forces the electron to shed its kinetic energy in the form of an X-ray photon.
Now, what's just wild is how inefficient this whole process is. Think about it. Only about 1% of all that energy we put into the electrons actually becomes useful X-rays. The other 99% just turns into heat. That's why the target, which is usually made of tungsten, often has to be rotated by a motor just to keep it from literally melting under all that heat. You know, the X-rays that come out aren't all the same. If you were to plot their intensity against their wavelength, you'd get a graph that looks something like this. You see that continuous curve? And then you've got these really distinct sharp peaks. That's a huge clue, and it tells us that there are actually 2 different physical processes going on at the exact same time.
That smooth curve is something called Bremsstrahlung, which is just German for braking radiation. This happens when one of our high-speed electrons zips past the nucleus of a target atom and gets deflected and slowed down by its electric field. It creates a whole spectrum of X-ray energies. But those sharp spikes? That's characteristic radiation. This is way more dramatic. It's when an incoming electron scores a direct hit, knocking an electron right out of an inner shell of a tungsten atom. An electron from a higher shell immediately drops down to fill that empty spot, and when it does, it releases a photon with a very specific energy, an energy that is a unique signature or characteristic of tungsten.
Okay, great. We've successfully created a beam of X-rays. Now for the really cool part. How do we use this invisible beam to create those black and white pictures we're all so familiar with? The whole magic trick boils down to one key principle: attenuation. Now, it's a bit of a fancy word, but all it really means is that the X-ray beam gets weaker as it passes through stuff. Some of the photons get absorbed, some get scattered, but the bottom line is fewer X-rays make it out the other side than went in.
And this right here is the absolute heart of X-ray imaging. Different parts of our body attenuate X-rays by different amounts. Really dense stuff, like our bones, are fantastic at absorbing X-rays. They stop a lot of them, and that casts a bright white shadow on the detector. Softer tissues, like muscle and fat, are less dense. They let more of the X-rays pass right through, so they show up in shades of gray or black. We can actually put a number on this stopping power. It's called the linear attenuation coefficient. Just look at the difference here. The value for bone is more than 3 times higher than it is for soft tissue. That huge difference is exactly why our bones show up so clearly and with such great contrast on an X-ray. But there's a catch. A standard X-ray has one big limitation. It's basically a flat 2D shadow of a 3D object. Everything gets squashed onto a single plane. You can't really tell if that spot is in front of the bone or behind it. To really see inside the body in true 3D, we need something a little more advanced.
And that brings us to the game changer, computed tomography, or what we all know as a CT scan. This is where we go from a simple shadow to a fully explorable three-dimensional digital model of the body. It's a whole new dimension, literally.
The best way to think about it is with a simple analogy. A regular X-ray is like a shadow puppet on a wall. It's flat and you lose all sense of depth. A CT scan, on the other hand, is like walking all the way around that puppet, taking pictures from every angle, and then using a computer to build a perfect 3D digital sculpture of it.
So a CT scanner is basically this big donut-shaped machine. Inside, there's an X-ray tube and a whole bunch of detectors on a spinning ring called a gantry. As you lie on a table that slowly moves through that ring, the gantry just spins and spins, taking hundreds of thin X-ray slice pictures from every possible angle around your body. What the computer does next is brilliant. It takes all of that data and digitally breaks down the scanned area into millions of tiny 3D cubes called voxels. You can think of them as volume pixels. And the computer's one massive job is to figure out the exact attenuation value for every single one of those millions of voxels. So, how on earth does it do that? Well, let's simplify it. Imagine we just have 4 voxels in a square. The scanner takes a measurement from one side, getting a total value for each path. Then it rotates a little bit and takes another set of measurements from a new angle. It just keeps doing this over and over, collecting projection data from all sides. Finally, this is where the real magic happens. A super powerful computer uses a complex mathematical algorithm to basically solve a massive puzzle. It works backwards from all those total measurements to figure out the correct value for each individual voxel. It's an incredible amount of calculation, which is why CT scanners only really became practical once computers got powerful enough to handle that kind of number crunching.
Okay, let's not be scared of the math here. We're going to take a quick look at the actual physics that underpins all this technology. We'll see how just a couple of simple formulas govern everything, from how powerful the X-rays are to how they get stopped by different materials. All right, first problem. Let's say we have an X-ray tube, and we're blasting electrons across it with 30,000 volts. The question is, what's the shortest possible wavelength, which also means the highest possible energy, of an X-ray photon we can create with this setup? The principle here is actually pretty straightforward. It's all about conservation of energy. The maximum energy an X-ray photon can have is equal to the total kinetic energy that the electron had just before it crashed. So we set the electron's energy equal to the photon's energy using this fundamental formula, and we can solve for that shortest, most powerful wavelength.
And when you crunch the numbers, you get an incredibly short wavelength, 4.14 times 10 to the minus 11 meters. That puts it squarely in the X-ray part of the electromagnetic spectrum.
Okay, next question. This time we're talking about attenuation. We're told the attenuation coefficient for copper, and we need to figure out the half thickness. In other words, how much copper do you need to cut the intensity of an X-ray beam in half? To solve this one, we use a classic exponential decay formula. It's a powerful little equation that tells us exactly how the beam's intensity drops as it goes through a material. We just pop in 50% or 0.5 for the reduction we want, and we can solve for the thickness needed to achieve it. And there it is. The result shows it takes just 1 single millimeter of copper to cut the beam's intensity by half. This is the exact principle engineers use to design effective radiation shielding. All right, we've gone through the physics and the math. Let's wrap things up by tackling some of the most common and most important questions people have about X-ray technology. This is probably the biggest question of all, right? How can this radiation be so good at seeing inside us, but also be something we have to be so careful with? It really is a double-edged sword. Their effectiveness comes from their incredible ability to pass through our soft tissue, but gets stopped by dense bone, which creates that vital contrast we need for an image. But the potential for harm comes from the exact same source, their energy. X-rays are a form of ionizing radiation. That means they pack enough punch to knock electrons right out of the atoms in our cells, which can damage our DNA. This is why medical doses are always kept as low as possible, and why a CT scan, which is basically hundreds of X-rays all at once, delivers a much higher dose than a single snapshot. So, given those risks, it's obviously critical that we have really solid safety measures in place. What do we actually do to keep everyone's exposure to a minimum? The principles are pretty straightforward. First, we use dense materials like lead for shielding. That's what those heavy aprons and protective screens are made of. We also keep the exposure time as short as humanly possible. The staff who operate the machines always maintain a safe distance or stand behind a protective barrier. And finally, the machines themselves are constantly calibrated and tested to make sure they're delivering the absolute minimum dose necessary for a good image.
So when you think about it, the progress has been absolutely breathtaking. We've gone from a simple, blurry shadow on a photographic plate to a fully interactive 3D digital model of our own anatomy. And it just leaves you with this final, fascinating question. Now that we've mastered this, what other invisible worlds will physics allow us to see next?